Guys, in the last video, we were talking about the column, and we said this column's got particles on the inside, right? And we've always talked about these particles, but we've really only focused on the surface of the particle and not really on the particle itself. So with that said, cations and anions have different columns on the side of the house, and I want to make sure that I'm choosing the proper column for the proper purpose. These particles are on the inside and they're covered in those functional groups. And we said that one had a sulfonate and one had ammonium. Well, those are just the little fingers that are sticking up off of the surface of the particle. That's not the particle only, right? So we need to talk about the material of the particle now. So again, if I had to draw it out, there's your column over to the right-hand side, and that column's got particles on it. And those particles, well, it could be loaded all over the surface, and that could be ammonium, or that could be our sulfonate group. All right, so this particle, not the fingers that are hanging off, they're going to come to us in two different forms. Most of the time we have a choice in ion chromatography where we can choose silica particles, or we can choose a polymer-based particle. Now, very early on, the silica was looked at as probably the prime choice because silica is like SiO2, and there's some polarity associated with this thing. And we knew that these were aqueous solutions most of the time. And aqueous solutions basically means the solvent was water, and water and polar mix. And they thought that the silica could do a very good job in separating and handling the aqueous mobile phase. And it does. It actually really does. The problem, though, is that the silica is not really as stable. And it can break down over time if I'm not careful. And there can be interactions with the silica that maybe I do not want. So I've got to be really careful when I look at the silica stationary phase. Because of that, the silica, well, it's not even really a choice anymore for us. Yeah, it's a great idea. It's a great concept. It worked at one point in time. But now, in today's laboratory, silica is not the way to go anymore. It's a polymer-based particle is what I would want to be using at this point. The problem is that the polymer-based is typically organic, okay? Polymers are basically organic molecules, and these polymers are basically linkages of one molecule to another molecule to another one to another one. And they can become three-dimensional, meaning that maybe every other one I could see another one that's sticking up, right? And then all the way through, I can get another chain that connects it down here. I mean, these things are three-dimensional in nature, and that's something that I have to deal with. The issue, though, is that very early on, the problem, and we've talked about this before, was how can we put aqueous samples onto a polymer, which is more organic and non-polar. And this was kind of hard to do in the beginning until they figured out how to modify the surface. As long as they modified the surface of this polymer, then we could inject aqueous samples on it without an issue. And those aqueous samples, because they were in water, is not going to cause us a problem. It's going to interact with the stationary phase particle, even though that particle is organic on the backbone. So these spheres, and it's kind of what they are if you go back and think about that picture that I showed you in maybe a handful of videos ago. But these spheres or particles are polymer-based. And this polymer-based particle has modifications on the surface, and these modifications will allow the aqueous sample to interact with it, right? Now, I told you that silica is not really used anymore. So what's the problem with them now? I kind of mentioned it already, but let me give you a few more reasons on why silica is something that you need to stay away from, all right? So number one, what we're going to find out is that silica can be used, but silica cannot be used in suppression. So basically what that means is if I'm running anions, silica is not the way to go. Silica has an interference with the suppressor unit, and it can contaminate the suppressor, and it will prevent the suppressor from doing its job. So the suppressor can become overloaded. The suppressor can start giving me a really high conductivity value. The suppressor is going to be kind of hard to get dislodged and cleaned out and to rinse. And it's all due to the silica particles that's on the inside of this column. It can release things, and maybe even the silica itself can go through and cause problems in the suppressor unit. So because IC is really used for anions, then the use of silica has dramatically plummeted already. I can use it for cations. It doesn't require a suppressor unit. But if I'm running anions, the typical anions that we always run and analyze for, then this silica is not going to work for us. Number two, they cannot withstand very high pH values. pH plays a role in the silica molecule, SiO2. And the pH can actually break down and start destroying the silica on the inside. It actually kind of reacts with it in a way. And it will slowly dissolve the silica in solution. Well, very high pH, well, let's take a look here. If my eluent is sodium hydroxide or potassium hydroxide, then I have an issue. And that's because those are alkali. And those alkalis have very high pH units. They're over 7. A lot of times they are running about a 10 or an 11. And this mobile phase is constantly pushed through the silica of the column. And that means over a course of time, this thing will slowly decompose, little bit by little bit by little bit by little bit. So what's happening is that the amount of your stationary phase will begin to change over a course of time because you're dissolving it. How awful is that? So silica, as you can gather, is really only used, if you're going to use it, for non-suppressed methods, which are typically cations. Cations, though, they analyze much better on other pieces of equipment. So I'm going to cross the cations out, and I'm going to say non-suppressed anions, because there are a few, but these are very rare. You will hardly run across them in a laboratory. So because of that, the silica is going to be very rare as well, and you will probably not run across it in a column packing for ion chromatography anytime soon. All right? Now, let's talk about the other option. The other option is going to be our polymer-based. So there's two versions here of polymer packing in a column. One is going to be styrene. All right, so styrene is going to be abbreviated with an S. And the other one is going to be called divinyl benzene. And this is going to be abbreviated with a DVB. Now let's talk about structure for a minute. If you have taken organic 2 at this point, styrene and divinyl benzene, they're probably molecules that you've seen or that you've been acquainted with. Actually, if you were in one of my organic classes, you would have memorized the structure of styrene at this point, along with a handful of other benzene-related structures that are pretty important. If I take a look at styrene, it is a benzene ring. There we go. And off this benzene ring, we're going to have a carbon double bonded to a carbon. This carbon double bonded carbon, this is called the vinyl group. And that is why this is called styrene or vinyl benzene. Styrene is more of a common name that's associated with the structure. We've got common names that we can use for things, right? So styrene is the common name for that particular thing. But I could also call this vinyl benzene. It's the same thing. So now you've made the connection. Because if you take a look at their other polymer, it says divinyl benzene. Oh, okay. Well, what they've done is that they've probably taken styrene, which is this benzene ring that has one vinyl group on it already, and they have put two vinyl groups on it. So there's my first one. Well, where's my second? Well, I have an option. They're not going to go side by side. These groups don't really like each other because of that double bond. Those are negative areas, and negative areas are going to repel. So I could draw maybe one over here, right? Skip one, draw it there. Or another option that I could see would be this benzene, and here is a vinyl, and it can go directly across from it. So this would be the meta position, because this is ortho, and this is meta, and this is going to be para. And this is my para position, because this is going to be ortho, that's going to be meta, and this is going to be para. Notice it would have worked the other way around too. Ortho, meta, para. That's the way benzene works, okay? So two versions of a polymer here. They're really kind of the same thing. One version has one vinyl group. That's it. The other version has two vinyl groups. And I've got kind of a choice here. I could get a vinyl group that skips one, and you got a neighbor beside of that one. Or I've got a choice where they live directly across the street from each other. All right? So these choices are good enough. That's all that we need. We don't need to make them any better. These polymers are going to start connecting together. And they're going to make a big, long chain of styrene, 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 or DVB, 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 DVB. One after another, after another, after another. I am going to write a third. It's not really that different, though. Sometimes people will actually combine these. This is a combination. And this is a combination of styrene and DVB both. So you might see an alternating one. Styrene, then DVB, then styrene, then DVB, then styrene, then DVB. You get the picture. But these are basically the particles that are making up the stationary phase on the inside of an ion chromatograph column. These are great. They're organic. So they're going to actually withstand very high pH levels. You know, benzene is pretty stable on its own. Benzene is delocalized. It's not going to be reactive that much. I mean, it's kind of a big boy in the chemistry world, and it can take care of its own, and it doesn't need to live with mom and dad anymore and mooch off of, you know, free room and board and, you know, nice meals prepped in the mornings. Benzene can take care of himself. And because of that, it can withstand quite a bit. And one of those things that it can withstand is high pH values. So this is going to actually be good for it. It can do this without a problem. That was the problem with silica, right? So if we're using NaOH or KOH as a mobile phase, it's not going to interfere with the particle. It's not going to dissolve them. It's not going to break them down. It's not going to destroy them. It's not going to make my column go nasty over a course of time. It's as simple as that. So S and DVB can do a very good job handling that alkali mobile phase that you might have to use on chromatography at some point in time. The issue is that these groups, especially in a polymer, these things are hydrophobic. They are organic, and they are mainly nonpolar. And we know that polar and nonpolar doesn't mix. So I've got water, and this water is going to be polar. And I'm going to expect that water to associate with the particle. And the particle's nonpolar. It's not going to keep that water around. If it doesn't keep the water solvent around, it's not going to keep the ions around either, whether it's cation or anion. So there's got to be a way that we can maybe make this more friendly. We've got to put some makeup on it. Okay, we got to make it a little more attractive, and it seems like makeup does that to some guys. I don't know why, but it does. So these particles, well, we're going to have to make them a little more attractive. We're going to have to let the hydrophobic and the or the water, that hydrophobic structure is going to have to become more hydrophilic instead. So we modify the surface. We put these pretty little functional groups on them, like positives and negatives. And that way the water comes around and the water sees what's on the face. That's it. Just face value. And those positives and negatives are there, and that water molecule will hang out, and those cations and anions will hang out on the surface. And that's really all they care about. I hate to say it, but they just care about what's on the surface. And then they go on to the next particle, to the next one, to the next one, to the next one. But all at the same time, these things can withstand very high pHs and they will not dissolve on us. And they can also withstand pretty high pressures. They are polymers. They are strength in numbers. These groups are holding hands with each other and they're clustering together. And you can do a lot with them. And it can withstand some pressure. So I can increase my flow rates. And my flow rate is not going to destroy that particle or break it apart. That polymer is going to hold its shape. It's going to hold its structure. It's not going to change over time. And that's good news for me, because I cannot have a stationary phase that's going to go through and change shape over a course of time just because it cannot withstand the high pressure that my system is giving it. All right? So let's take a look at this styrene and divinyl benzene structure a little bit more. I've got a picture I need to show you. And this artistic ability is a little bit better than mine, okay? So what you're seeing here on the screen is a combination of the S and the DVB structure on the PowerPoint slide. So here you're basically seeing a carbon backbone, right? Carbon, 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 all the way through. So this is kind of our railroad track right there. And then off of this track, we're going to have basically a divinyl benzene group. So here we're going, just a second. The divinyl benzene, I'll talk about this in just a second. The styrene group, which is the benzene ring that's here. And then off of this is your C double bond O. All right. And then here, what you're seeing is another styrene. So here we see a benzene ring, and then off of this is a double bond, carbon double bond. So that's what we're seeing here. That's an S and that's an S. This is supposed to be the DVB. And you're probably wondering, well, wait a minute. You told me that there were going to be two of those, right? Or one of those. What's going on here? I don't understand. Well, what they're showing you here is that there's a benzene in place. And this benzene has a group that's hanging off of it. And this group is going to be a continuation of the other chain of the house. So this is actually a linkage here. So the S in the DVB, this is an S structure, this is an S structure. This structure, well, that could have been a carbon that was double bonded to another carbon, but maybe that bond was broken, and that's going to allow the polymer to continue on this side to make another railroad track, so that way the process is going to happen as far as building a polymer up. The problem here with the slide is that the DVB is not properly represented in a way. So sometimes I would see a styrene like this, and then maybe every now and then I would see a double bonded carbon coming out, a double bonded carbon coming out at another location somewhere within the chain, but that gives you an idea of kind of how this thing is going to be happening, right? Some people would also look at this benzene ring and they would see this carbon that's going to be there, and they would say, well, maybe that was kind of a double bond at one point, but this double bond was broken to allow that carbon connection, and this opened up a carbon bond over here that could relate to another one. So there's another kind of instance where the DVB structure could have been modified and changed a little bit to make this system work. Overall, though, what I want you to take away from this is that this is kind of how a particle is made. That is what a polymer is. And you're seeing X, Y, and Z, meaning that these pieces can repeat over and over and over for however many numbers that they need to repeat for. But all of these structures are coming together to make one big happy chained molecule. And that is what we call our stationary phase particle. So they are polymer based. They withstand high pressure. They withstand high pH. They're not going to be modified, but they are organic. And they're made up of these polymers of styrene, divinyl benzene, or a mixture of both. Okay? In addition to that, these things are going to be modified on the surface. So let's say that up here at the top, this is the surface. They're going to start slapping NH4s onto the surface of this particle if it's an anion column. They're going to start slapping SO3s onto the surface of this particle if it's a cation column. And this we've already talked about in previous videos. All right. So now we're talking about the surface that those functional groups are attached to. And that's how we do that. All right. So that's the difference between the particle and the surface of the particle, which is a little different. And that is why these particles become slightly hydrophilic, because of those charged surface areas that are on the outside of that spherical particle on the inside of your column. And that is what does the separation for you, folks. It's as pretty and easy as that. I hope it's easy at least.